Uh, yeah, so I think the recording has started. All right, cool. I will also share my screen now. Let me know when the screen is visible, okay? Is it visible, the screen?
Yes, yes, it is.
Okay, okay, fine. So, all right, so, yeah. Okay, so, hello, namaste, and welcome everyone. Uh, So, so unfortunately, we had a long hiatus with these lectures. I'm sorry for that. I was also kind of ill. I had some cold, and because of that, I was not able to, continue with these lectures. Nonetheless, for better or worse, it was okay that last time we had covered all the preliminary, so it's kind of we can start with the actual machine learning part, though we are a lot late, but okay, but I mean it's fine. Nonetheless, we will start. I will recap the stuff that we covered last time, and we will continue with it for like 15 minutes, and after that we will switch to the machine learning part. And after then we won't be requiring we won't come back to this part. It will be used as a tool for our upcoming lectures. Okay, so just to recap, so last time we were looking at some basics of information theory, and we sort of uh, so we sort of try to convince ourselves that okay, what do we actually mean by information. And we came up with some we saw some examples, and we actually saw that okay, information, the word information has meaning only when there is some sort of randomness. If there is no randomness, for example in this case when the two sides of a coin are heads, there is no information that one can provide to me. And to capture this information, we came up with the notion of entropy. I didn't tell you how the derivation of the expression for entropy, which is this following thing. However, to convince you that okay, this example does make sense, we took some examples. We took in particular, we took example of a fair coin and a biased coin, and we sort of saw that okay, the randomness in a fair coin is more, I mean, as it is expected, because both the sides are equally likely. However, in a biased coin, one side is more likely, and hence there is less randomness. And in that case, we expected that okay, the entropy for a fair coin should be high, and the entropy for a biased coin should be low. And at least saw that okay, we did observe this phenomena when we substituted those values and calculated the entropy. Then we saw that okay, entropy is nothing special. I mean, we can define it for a joint random variable x comma y as well. And we sort of came up with this notion of joint entropy, where the joint entropy, instead of in the formula of joint entropy, basically instead of substituting just the p of x, we used the joint distribution p of x comma y. And similarly, we came up we kind of defined the notion of conditional entropy in the. So for example, in a situation where you have a random system, where you know the value of few of the variables, random variables, but you don't know the uh, values of the other random variables. In that case, given some information about known random variable x, what can you say about the random variable y? We saw this is I sort of told you that okay, this is the formula for it, and we tried to make sense of why this formula should why is this formula good. And we sort of saw that okay, eventually it boils down to this formula. I mean, we won't be using conditional entropy in our machine learning part. Nonetheless, it is a good thing to know that okay, something like this does exist. And we sort of saw this chain rule for joint entropy, which is again a fun thing to know. And in particular, we saw that okay, whatever formula you have for the joint distribution, the entropy behaves like in some sense entropy behaves like the log of it. Okay, so you take log here, and log so and you take log here of this entire whole thing, you will get summations of individual conditional distributions, and that is what entropy, chain rule for entropy, shows you. Okay, and after that we came to an important definition, which was that of the relative entropy. So the idea of relative entropy is to, in some sense, can we come up with some notion of, how close two distributions are. So let's say P and Q are two distributions. uh, is there some way, we can quantify, are P and Q close, or are P and Q far away, or things like that. So Kale divergence or relative entropy uh, is a metric. Okay, is a divergence metric which actually does that. Okay, so the expression for relative entropy or Kale divergence is the following. So it is summation of P of, so dp and q. So we define the divergence by this symbol, you know and it is given by this formula, summation over x, px log px by qx. Okay, now again, I didn't derive this thing, because if we start deriving this expression, it will be a big deviation from our main goal. So what we instead saw was, okay, can I convince you that, okay, this does make sense, this formula does make sense. So instead what we did was, we again took some example. So we said that, okay, let's say P is a distribution which assigns half to 0 and 1. Q is a distribution which again assigns half and half to 0 and 1. So we can clearly see that P and Q are actually the same here. So if this divergence metric is to make any sense to us, the divergence between P and Q in this case should be 0. And we saw that, okay, we calculated this and we saw that it actually comes out to be 0. So yeah, so I mean, at least the desired property of of closeness between two distribution is satisfied by this metric. In particular, you can see that whenever px and qx are equal, this term will become 1, and log of 1 is equal to 0, and hence the entire expression will actually become 0. So it does make sense to use this distribution, use this metric. So further, what we did was that, okay, we saw the case for a we saw the case where both P and Q are equal. However, what if P and Q are not equal, right? And in that case, we again did some calculation and it came out to be 0.65. And we saw that, okay, so if P and Q are not equal, it does give us some value, okay, which is non-negative. Non-negativity is something again that we desire from a metric, okay. So we had covered things till here. So what I will do is, for let's say for next 15 minutes or so, I will continue this topic, okay, and after that we will switch to the ML part and we will sort of continue it from there, okay. So okay, so if you didn't understand anything, the key takeaways are, uh, if I had to somehow, summarize that, okay, let's say if you didn't understand anything, what should you take home? You should take home the maybe the idea of entropy, which is easy to understand. I hope that part is clear. You can ignore joint entropy, conditional entropy, and these things, but however, you cannot ignore relative entropy. Relative entropy is a very crucial term which pops up, every now and then whenever you are dealing with ML, or in general mathematics. Scale divergence has a significant role to play, okay. So if I have to say that, okay, what the most important thing from all this lecture, you should perhaps remember what relative entropy or Kale divergence is. So Kale divergence, there were two people, Kullback and Leibler. These two people came up with this metric, this divergence metric, and Hence it is called KL divergence. People generally call it KL divergence, and we will also call it KL divergence. Okay, relative entropy is something that information theorists use. Nonetheless, we are not information theorists. We will be using this in machine learning, so we will be using KL divergence. So just keep this in mind. Okay. So there are few properties about KL divergence that we should know. Okay, and which are sort of important for us as well. So the first property that I would like you to tell is okay, I would like you to know is that okay, so is KL divergence a distance? So just to recap your walk through your memory, what is a distance? If you remember, so can I call any distance? So let's say I have a function d which goes from, let's say, r to r. Okay, can I call any function which goes from r to r as distance? Well, no, it needs to satisfy few properties. Okay, so sorry, it's not r to r, it's r cross r to r. What do I mean by r cross r? I mean it should take some two values x comma y as input, and it should give d of x comma y, which is a scalar value as output. That is what I mean. So can any such function be a distance? Well, the answer is no. And this is something that people often make mistake in. Any function which takes two values and inputs and spits out a real number cannot be a distance. It has to satisfy several properties. I will just jog your memory and I will tell you what are those properties. The first property that it should satisfy is that d of, let's say, x comma y should be greater than or equal to 0. Okay, so it should be non-negative. If the value it takes is negative, then it is not a distance. Okay, and not just that, dx comma y should be 0 if and only if x is equal to y. Okay, so this is one property of distance. We know this already. For example, when we use, so let's say you have a real line. Okay, so let's say this is your real line and there are two values x and y. And if I say, okay, let me define your distance as dx y is equal to dx minus y, is this a correct, is this a valid distance metric? Well, the answer is no. Why no? Because let's say I take x it to be, let's say 2 and y to be 5. This will become minus 3 and this is less than 0. And we see that, the distance cannot be less than 0. It should be non-negative. So you can say that, okay, well, this didn't work. So can I use d of x comma y to be mod of x comma y? Well, this will work because mod of 2 minus 5 is equal to 3. Also, we can see that when this is equal to 0, this would imply that x is equal to y. Okay. So the value of mod x comma x minus y will be 0 only if x is equal to y. So yeah, absolute value can work as a distance function on real line. Okay. So this was the first property. The second property that it should satisfy is that it should be symmetric. So what we mean by symmetric, d of x comma y should be equal to d of y comma x. This is another property. So I don't want that, okay, so if I take distance between 2 comma 5 and I take distance between 5 comma 2, they are not equal. I don't want this to happen. I want them to be same, because intuitively, it does make sense that distance is something that should not depend on the order of the inputs. Okay, so that is another property. And third property, which people often miss, is the triangle inequality. Triangles inequality. Triangle inequality property. What does it say? It says that, okay, if I take let's say there are three points x, y, and z, and distance between x comma y should be less than or equal to d of x comma z plus d of z comma y. So what does this mean? So let's consider an R2 plane. Okay, and you have 2 points. Let's say this is x, this is y, and this is z. Okay, and I hope you can see that any 3 points will make a triangle in this plane. Okay, uh, so if I take any one distance, let's say I take this distance L1 and I take this distance L2, the sum of L1 and L2 will always be greater than the third side, should be greater than or equal to L3. This is what it means. So this is another property that has to be satisfied by a distance metric. Okay, so I just jogged your memory through, these three properties. These three properties is something that you should know. And even in interviews and things like that, so I remember when I was at my college, my guide told me that one of the questions that he was asked for professorship in IIT was this same thing, that okay, what are the characteristics or properties of a distance metric. So these things are something that come in handy. Okay, just remember them. So okay, so all of that is fine. So coming to our question, that okay, this divergence formula that I just wrote, that we wrote here, is this a distance metric? This is the question. So well, let me give you the answer first. The answer is, well, no. KL, let me just write it as this. DKL is not a distance metric. Okay. Well, you can ask why. Prove. You can ask me to prove this to you. So well, what I will do is, okay, consider. So except for the, so it won't. So let me give you a spoiler. Second and third properties are not satisfied by KL divergence. Okay, it only satisfies this property. Just remember that. But nonetheless, I will give you this thing. I will show you. So let's say DKL and between P and Q. Okay, what was this? We just saw this to be equal to sum over x px log p of x by q of x. Okay. Now let us see. Look at the, what if I change the order of p and q? What if I take this thing? Okay. What does this become? This would become q of x log q of x by p of x. Okay. This is what it will become. So are these two equal? So well, one way to check this is, what if I subtract these two expressions? Okay, if I subtract these two expressions and the answer comes out to be zero, then these two are equal, right? So let me do that. DKL between PQ minus DKL between Q and P. What will this become? This will become summation over X. I hope you can see that. So let me write it. P of X log Px by Qx minus summation over X Qx log Qx by Px. Okay. So I will just do some simplifications now. Okay. So I won't write X now. I hope that it is understood. I will abuse the notations a bit. So instead of minus, I will do this plus, and what I will do is I will take Q. No, I will take the inverse of this, and minus sign will come out, right? So what I did, this was actually Q by P, which was here. So I took the inverse of it. So minus sign will come out, and that will club with the minus sign that was already here, and it will become plus. Okay. Now I can club the two summations because both of them are summed over x. So I can combine individual terms. So this will become this p of x plus q of x log p of x by q of x. This is what it becomes. Okay. So I hope you can see that this term, uh, if p and q are not equal, okay, if p and q are not equal, then this term can never be equal to zero. Why? Because this term won't be equal to zero, right? Because p and q are not equal. This means that this term won't be equal to one, and hence this term won't be equal to zero. And this term, we know that p of x is not equal to q of x, right? So this sum, and we know that P and Q are always positive because they are distributions. This will be always greater than or equal to 0. So this will again not be equal. So this will again, I mean, I hope you can see that this will always be greater than 0, and hence this is not equal to 0. Okay. All right. So I hope this is enough to justify. This is enough to convince that KL divergence is not a distance metric. That is one reason why it is called divergence. Okay, it is not called KL distance. It is called KL divergence. There is a reason behind calling this a divergence, because it is not a distance. Just because it is not a distance, we are calling it divergence. Okay. So this is a subtle thing, but nonetheless, we should keep this in mind. Okay. Okay. So this was the first point. Okay. First property, so to say. Let me write the second property. The second property, as I said, that KL divergence is not a distance metric. Nonetheless, it satisfies this first property that that we discussed here. This property. So I will write that down. I will just write that down. So KL divergence between two distribution P and Q is greater than or equal to 0. Okay, with equality, with equality, if and only if P is equal to Q. Okay. I think so. I think this is all. So these are, I think, the three properties that you should know. Okay. There are many more such things that I can tell you, but I think this is enough for us to sort of stop and uh, kind of move on. Maybe what I will, so okay, fine. Let's not do that. Maybe I will do it if it's required. I will do that. So if you have any questions still here, maybe you can ask them. Okay. So now I will move from information theory, probability theory, and all those things to actual machine learning. We won't waste our time. I mean, we are not wasting our time, but I mean, we won't
Yes.
divert to this part. Okay.
Okay.
So if there is any question, you can ask me, or else we can move on. Okay.
No, we can move on.
Okay. Fine. So so fine. So moving on. What we will now start is actual machine learning. Okay. Uh, so let me just write it down. Machine learning. Okay. Uh, okay. So okay, fine. Right. So, okay, I mean, I hope all of us know that, okay, broadly what machine learning means, okay, more or less, or even vaguely, we know what machine learning is, or I mean, what it means, okay. So, what it means is basically, so there is some data that is given to, okay, so so whatever I'm saying right now is a very vague thing, okay. This is just to give you some idea of what machine learning is. I hope that you already know these things. Nonetheless, I will repeat it, okay. So machine learning is basically, the idea is that you have some data, okay, and there is something that you want to predict in some sense, and since you have some data from past, you want to use this data and come up with an algorithm which can, using this data, come up with a, decision rule or prediction rule, such that it can predict the future instances. Okay. So 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 okay, fine. What I will do is, I will get straight to it. Okay. First, let me start with something called, so there are basically two paradigms of machine learning. Okay. Or learning in general. Let me not call it machine learning, because it is not a machine that learns. It is mathematics that helps us learn. Okay. let me just call it learning problem. There are two types of learning problem. Okay. So the first is what we call supervised learning, and the second thing is unsupervised learning. What these are, we will discuss it later on. Okay. For the time being, I just wanted to put it out there that okay, there are these two types of learning paradigms that we have in general. Okay. Now, what I so uh, uh, okay, what I will do is I will define some notions. Okay, some definitions, so to say. So let us first see. So I think all of you know what these things are, but I am just formally defining it. Okay, just to make sure that we are on the same page, just to set a ground level. I will just define few steps. Okay, so the first thing is something called domain set. Okay, so what is a domain set? It is denoted by this a calligraphic X. Okay, it is a set of objects. Okay, set of objects that we wish to classify. So right now we are sort of looking at the classification problem. Nonetheless, we will see afterwards that the problem need not be of classification only. It can be anything. But for the time being, let us just look at the classification problem. Okay. So a set of objects that we wish to classify or label. Okay. This is what we call as domain set. For example, let's say if you have a image. Okay. So let's say you have an image and its dimension is, let's say, m cross n. So its height is n. So the height of the image is n and width is m. It can also have some channels, but for the time being, let's assume a single channel image. So each of its element is what we call as pixels. Okay. So it has some m cross n pixels. Okay. So what we can do is, convert it into a one vector, one long vector. What do I mean by converting it into a long vector? What I will do is I will just take all this row, all the pixels in this row, stack them here. Okay. Take the pixels of this second row, stack them again here, and so on. Okay. And I make a big vector out of it. So this will be a vector in what, m cross n, right? So since there are the dimension of the image is m cross n, the number of pixels will be m times n, right? So this will be, so let's say I had capital N such images, so I will have n such vectors, right? Capital N such vectors. Okay. So this is what my domain set will be, right? So these are images that I want to classify. So that is my domain set here in this case. Okay, the images here are my domain set. If you have doubt at any point, you can just unmute yourself and ask. Okay. The second thing that I wanted to define was a label set. Okay. A label set is denoted by calligraphic Y. Okay. So basically, label set is nothing but the number of labels that you have. Okay. Uh, Labels that we want to assign. Maybe I should write of set of labels that we want to assign. So for example, if you have an image and let's say uh, so in let's take an example of medical images. Okay. So you have, let's say, uh, 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 what is it called, I don't remember the exact thing, but let's say you have some lung uh, So let's say you have some MRI images, okay, MRI images, and given the images you have to basically so these are let's say MRI images of let's say lungs, okay, and you want to basically you are asked that okay you have to classify whether the given image has cancer or not, okay, so cancer or not, okay, so the cancerous images what we call is normal images, normal or benign is what the word is used. If not, it is called malignant, okay. Okay, so basically you have to basically classify if the given image is benign or malignant. In that case you have two sets, right? I mean you have two the label set that you have is of the size of 2. uh, so you can either represent it by just a set 0 comma 1, so you can say that okay if there is no cancer, the patient is completely normal, you can assign it a label of 0, or if not then you can assign it a label of 1, okay, like an indicator function. Okay, it has cancer, then 1; it doesn't have cancer, then 0, things like that. But you can even have examples where you don't the label set is not binary. So this is basically binary, right? I mean either 0 or 1. However, it is not necessary that the given problem is binary classification. It can be multi-class classification problem as well. For example, it can be something like 0, 1, 2, 3 till some k. So, for example, if you are asked to identify the species of a bird, there are several types of species, right? It need not be just you cannot classify it into two labels. You will need as many labels as there are species of that bird. Okay. So in that sense, it can be multi. So this is multi-class, multi-class. Okay. So this is this would be a multi-class classification problem. Or it need not be discrete even, right? I mean in this case you had two examples. Here there are k labels, okay, but in some sense you this need not be discrete, it can be continuous as well. So for example I can take rm as my label set. So one possible you can ask me of an example. So the example would be, for example, consider, so let's say given some features like how many rooms a flat has, how many kitchens it has, and how much square foot the area is, and things like that. Someone asks me that, okay, tell me the predicted price of a particular house apartment. Okay, so in that case, the price could be anything, right? It can be 80 lakhs, 80 lakh, 5,000 something. I mean, it can be anything on the real line. Okay. So you can see that now my label set is not discrete. It is a continuous set, and it can take any value. I can put my price to be 80 lakh point something. Okay, it's up to me basically. So in that case uh, my classification task need not have discrete set of labels. It can have a continuous set of labels as well. So uh, let me just write it down. Okay, if your label set is discrete, okay, if you have discrete label set, this we generally call this as classification problem. Okay, where you have to basically, so it's like you have k bins and you have to put your you have to choose one of the k bins. Okay, so it is like classification. You have to classify your given input as one of the k types. However, if it is a continuous one, if your label set is continuous, then what we call it is a regression task. Okay, so price prediction is a regression task where you have to, the set of labels is continuous and there is no classification involved. However, you have to, uh, predict something which is continuous, in that is what we call as regress. Okay. And given these two, you can now define what your training data is. Okay. What is your training data? Training data, let's define it, let's note it by S. Okay. It is basically a sequence of pairs. Okay. So x1 comma y1, uh, x2 comma y2, x3 comma y3, till let's say some xn comma yn. So what is it? It is a finite. Okay. It cannot be infinite. Okay. It should be finite. Finite sequence of pairs in x cross y. Okay. So what does it mean? You take one sample from x, you take another sample from y. X is what? Your domain set. This x is your domain set. Okay. And y is your label set. You take one sample from each of them. So x1, you took x1 and y1 from them. So that is one pair. You took another x2 and y2 from it. It's the second pair, third pair, and so on. So a finite sequence of such pairs is what is your training data. Okay. So this is something that we already knew, but I just formalized it. Okay. There is nothing new here. Then what we have is something called data generation model. So now I would like you to, pay some attention. What I'm going to say next is might be a bit confusing, but let me tell it. Okay. So okay, use other color. Assume there exists a labeling function f that goes from x to y. This is an unknown function. Okay. Or in other words, I there is for each yi, I can write it as a function
Hello.
of
Hello.
yeah, yeah.
You Piyush, your voice is breaking.
uh is it breaking now as well?
No, not now, but when you were trying to write or something, your voice gets very low.
Okay. Can you let me know when next time it happens? Maybe I was not speaking
Yeah.
for some time. Maybe that's why you felt that my voice is breaking.
No, 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 no. Right now, currently it was breaking, so that's why.
Okay. So next time, as soon as you feel that my voice is breaking, just let me know. I will do something. Okay.
Yeah, it's breaking right
Okay, sure. So, this idea. So here is the big idea. Okay, the idea is that there is some God. Okay, or let's call it nature. Okay, whatever classification problem that we see in life. Okay, has a inherent labeling function to it. Okay, what do we mean by this?
now.
Sorry.
Your voice is not clear,
Okay,
Piyush.
so let me change the mic maybe. Okay, give me a second. Okay.
Okay.
So, is it better now, Jason?
No,
Is it okay?
no, it is not okay. It is very much.
It's still noisy, is it? So is this the problem faced by, is it with you only, or is it with other people as well? Can someone,
Everyone,
because
uh,
I also cannot hear your voice clearly. There is some glitch in your voice as well.
okay,
So, is it possible that it is because of your internet connection?
let me check. Because we are connected in the same Wi-Fi, so maybe there may be a problem with that. Let me just switch to Wi-Fi.
So I am not able to interpret your voice because it is breaking a lot. Uh, so can someone else, some other participant confirm if my voice is audible clearly or not? Uh, Someone other than
Yes,
Jason.
you're audible.
Okay.
Network maybe.
Sorry.
You are audible to me. Maybe there's some issue in Jasel's network.
Okay. Yeah, that is what I feel as well because today the connection was pretty good. So
Yeah, yeah.
I don't think
I
that
I
there is.
No,
switched
it's
to the
fine.
I
Fine.
switched to I switched to Wi-Fi network. Now you are audible. Am I audible?
Okay. Yeah. Now
Yeah.
you are a bit, you are more interpretable. Yeah.
Yeah, okay, thank
All right. All right. Okay. So what I was saying was the following. Okay. So whatever classification problem that we see, so this notion of data generation model, okay, this in some sense, tries to what should I say? So, for example, let's say you are given a task of, classifying cats and dogs. Okay. So how do we exactly know? So let's say humans are, humans are like the best machine learning algorithm that there is. Okay. What do I mean by that? I mean that, okay, humans can classify cats and dogs with 100% accuracy, right? Well, then, what is there? I mean, there must be some feature that we see, right? I mean, there should be something that, okay, dogs are maybe, they have larger heights than cats. Okay, their facial structure is different than cats in a particular way, right? And all these stuff. There are some features in a dog's image that makes that which helps us to classify it as dog, and there are certain features in cat's image which allows us to classify them as cats. So this notion that, okay, dogs are dogs and cats are actually cats. Okay, what do I mean by dogs are dogs? The image of a dog is actually a dog. How do we know that? There is some feature that allows us to allows us to make a judgment. Similarly, there is an image of a cat is a we can classify it as a cat because there are certain features there which makes our judgment bend towards cat. So the idea of data generation model says that, okay, there is a god. Okay, there is so let's say that there is nature. Okay, nature has made these features. Okay, nature has assigned these labels in some sense. Okay, and how nature assigns this label? So nature assigns, let's say, an image of a dog. So there is some image of a dog. It assigns it a label of dog. Okay, and this labeling is done via function f, is what it says. Okay, so we don't know what this function is. Okay, so this is really why I said that there is some god which actually tells us that, okay, this particular animal that you see is actually a dog, or this particular animal that you see is actually a cat. How do we know that? There is some god that has told us this thing. This is what this data generation model actually says. And the way it is formalized is that this function f is present. Okay, however, we don't know this function. Okay, if we knew this function, then, okay, the entire goal of machine learning is lost. If we knew what this function is, if we knew how to map an image of a dog to actually the label of a dog, okay, then, I mean, let's just use this function, right? I mean, why do you need to do all this machine learning? Just use this function. If you knew this function, just use this function. Okay, and uh, so whenever you get an image x, use this function and tell whatever the output is, and predict that. There is all the issue, all the problems are done. However, this is the entire problem, that we don't know what this function is. Okay, so I hope I was clear. If not, maybe you can interrupt me and ask questions. Okay, so this is the idea, that there is a labeling function f which does this mapping. Okay, and this is what a data generation model is. This is how your data is actually generated, that there is a function f, you give it a input x, and it gives you an output y. This is how x comma y pairs that we discussed here are actually generated by nature or by god, whatever you want to call it. Okay, so now assume that x has some distribution, let's say px. Okay, and y has some distribution py of y. Okay, so this is not a correct way to write it, but let me correct it. So this is how we write it, that they are coming from some distribution, right? So what I mean is, what I am now saying is that, okay, this domain set things, whatever we saw here, these are actually a random variable. Okay, and it has some distribution that we again don't know. Okay, again we don't know what px of x is, that I wrote here. And similarly, this label set y is again a random variable, which is coming from another distribution py of y. We we don't know any of these distribution. Okay, just to make it clear, but we can always say that, okay, there is some distribution. We don't know what the distribution is, but nonetheless there exists some distribution. This is some hypothesis that I'm making. Okay, now, so if there are two random variables x and y, there will always be a joint distribution as well. Okay, as we discussed in our probability theory part, that if x and y are sort of two random variables, we can always write their joint distribution. So we can say that, there exists some distribution, pxy, joint distribution over x cross y, right? So this is nothing but just saying that two random variables will always have a joint distribution. Okay, now uh, the next formalism that we will make is that s, your training data is sampled IID from pxy. So what do I mean by this? What I mean is that, okay, pxy was some joint distribution. Okay, your training data that you have here, this complete training data, is nothing but samples from this joint distribution, is what it is saying. Okay, so what do we mean by sampling? I hope you remember that, so for example, let's say I have a Gaussian. So let's say I have a Gaussian distribution, and I sample some points from it. So this distribution will give me some points, let's say x1, x2, things like that, xn. So these are sampled points from this distribution. That is what we mean by sampling. So if you are given a distribution and you get some points from it, you can say that you have sampled those points from that distribution. Similarly, as what we saw here, this training data is nothing but actually points that are sampled from this joint distribution. And apart, they are not just sampled, they are actually sampled IID. What do we mean by IID? We discussed in probability theory as well, that they are uh, independent, dependent, and identically distributed. Identically distributed. What do we mean by this? That let's say I took some point, I sampled first point x1 comma y1 from this distribution. I sampled another point x2 comma y2. Now these two samples are independent from each other. That is what I mean. Okay, So they don't have any correlation between each other. What do we mean by identically distributed? Identically distributed means that x1 comma y1, if I sampled from pxy, okay, and I sampled x2 comma y2, this is also coming from the same distribution pxy. This is what we mean. So for pxy you can think of some normal distribution or something like this, okay, but the idea is clear, right, that the two sample points are not connected to each other or related to each other in any sense. They are independent, and further they belong to the same distribution pxy. That is all we are saying. So I hope you can see that this is just formalism. What do I mean by formalism? This is something that we already knew what we mean, okay, we knew what a training data set is and things like that. This is just a mathematical way to, write things down. That's all, nothing else. Okay. Okay, so now so let me make it clear that we know neither neither f, the labeling function that we discussed, nor pxy, that joint distribution that we are talking about here, okay. But there is a but we have samples. We have samples from pxy. So, and what do we call these samples? These samples is what we call as training data. Okay. So this is the setup. So I have made a, setup for you, that okay, there is some labeling function that we don't know what it is. There is some joint distribution that also we don't know. However, we have samples from this distribution that we are calling our training data, and using this training data we will do stuff. That's all. Okay. So I hope the setup is clear. If not, please ask questions, okay? Because this is something which is crucial and will come in handy, okay? Now, let me define what machine learning or learning problem in general is, okay? So what is a learning problem? Learning problem. What is a learning problem? Okay. So let me just write it down, okay? Prediction. Prediction rule is what some people call it, prediction rule. Some people call it classifier. Some people call it regressor, or some people even call it hypothesis. Depending on which field you are working in, these are different terms that are given. Okay, which is learning problem is just this. Okay, x to y. Okay, so this is some function h. I'm not telling you what it is, but let me write few things first. Okay, so given s, okay, your training data, which is drawn IID from an unknown pxy. Okay, so as I said, as I promised you, that we won't know anything about pxy, but we have samples from it which we are calling s. Okay, output. So this is our goal. What I'm going to write down is our goal. Output a h that belongs to some hypothesis class h, where uh, h is a family of hypothesis functions. Okay, so a lot of things I have written down, but let me just explain to you what it is. Okay, so I hope you can. So I hope this till this part everything was clear. So what we are trying to do now is, we are trying to formally define what a learning problem is. Okay, so the way it is defined is as follows. Okay, so you have two domains, x and y, your domain set and your label set. Okay, and I can make I can make any function from these two. So I can create any function that takes this as input and outputs something from this domain as output. Okay, I can make any such function. But are all these functions good? No, right? all of these functions are not good. Few of them are good and few of them are bad. For example, let's say, like, coming to our cats and dogs problem. So let's say I have two images. I have three images, let's say. Okay, so this is dog, this is dog, this is again, so okay, maybe this is cat. Okay, this is cat. Okay, now I have a label set. Let's say this is which I am saying, let's say 0 is denoted by dog and 1 is denoted by cat. I can create a function like this, right? This can be my function f, or sorry, this is h. So what my function will do is, it will take some dog image and output tell it is dog. It will take another dog's image, which is this one, and tell it as cat. It will take another cat image and tell it as cat. This can be a function. No one can stop me from making this function, right? After all, function is nothing but, assigning something from here to this, from here, from this label to this set, right? I can make a function like this. No one can stop me from that. However, is this function good? Well, no, this is a trash function because it is saying my this dog image is cat. Well, it is, since we know it is not a cat, it is not a good function, right? So I hope you can understand this part, what I have written here. There can be, infinitely many functions that can map x to y. Okay. However, all of them are not good. So how is a learning problem defined? So the learning problem is just saying that you are given some training data S, which is drawn from some unknown pxy that we know. So pxy we don't know, but we know that it is drawn from some unknown distribution. The goal is to predict a function h. Okay, the goal is finally to predict a function h, to output a function h, and h is actually belonging to some hypothesis function. So there are so how do I So let me just illustrate what I mean by this capital H that I have written here. Okay. So let's say I have some inputs I1, I2, I3, I4. Okay. Okay. Hope this is fine. Okay. And there are, let's say, two labels, 0 and 1. Okay. What I can do is I can assign this as 0, 0, 0, 1. This can be 1, 1, 0, 0, 0, 0. I can assign all of them 0, all of them 1, whatever. Okay. 0, 1, 0, 1, things like that. So let's say these were your inputs. You can think of this, maybe this is a dog image, this is again a dog image, this is a cat image, this is again a, let's say, cat image. Okay, and 0 belongs to, let's say, dog, and 1 belongs to cat. So this is my label set. So I can, so this let's call let me so this is my function h1. Okay, what it does is it assigns 0 to this first input. It assigns 0 to the second input, assigns 0 to this third input, which is actually a cat. However, it assigns 1 to this last input, which is a cat. Okay, this can be my h1. Similarly, I can say, someone can say that, okay, why should I use your h1? I can make my own function, and this is my h2. Okay, someone can again come and give me this third function, h3, h4, or h5. These kind of things. Okay, so I hope you can see that if I use what is my so if I make a family of functions 0, 1, there are four inputs, right, to the power 4. What it means is that it will, so this is basically a vector of 4 cross 1, where each of its can be either 0 or 1. Okay, so this is my h in this case. Okay, this is my h in this case, that all the possible functions that can either be 0 or 1, in one of these places, is my hypothesis function, is my hypothesis class. Okay, I can take any of these functions, for example h1, h2, h3, h4, h5, and that will be a valid function which I have described here. So I hope you will agree that when the function, this function 0011, this would be an appropriate function, right? Because it assigns 0 to dog images and 1 to cat images. So this is a perfect good classifier, or good function. So this is my h6. So I hope you can see that in this function there are a lot of trash functions, which are these ones, h1 to h5, and there are some good functions like h6. Okay, so the learning problem says that okay, so given your training data, you have to create such a function. Okay, you have to create such functions which are coming from this hypothesis class. That is all it is saying. Okay, if this is not clear, you can ask questions. Okay, because this might be confusing at first, but if not, we can continue. So note that learning problem doesn't tell it only asks us to get a output, get an output h. Okay, one such function. It tells us nothing whether it is good function or bad function. So I hope you can see that there is some gap. Learning problem is not all complete by itself. To complete it, we need to define something called goal of learning. So one can ask, why are these two separate things? Why are not they clubbed in one thing? Well, because your goal of learning can vary. Okay, I mean, sometimes your goal of learning can be classification, fine, but in some cases it might not be classification. It can be something else. Let me write it down, then we can say. Okay, then it will be more clear. Well, what is goal of learning? It is in some sense, measure of success, success or failure. And how is it defined? How we define a measure of success or failure? It is defined using something called loss function. Okay, so loss function is again a function that goes from your label set cross h of x, okay, to r plus. So let us wait and let us examine this thing. Okay, what it is taking your actual label y as in one of its inputs, and another input is h of x. What is h of x? H of x is something that we defined here, right? So it is one function that takes x as inputs and outputs something in y. So the loss function takes your actual out the desired output and your predicted output as input, and spits something spits a positive no, integer, positive number, positive real number out of it. Okay, this is your loss function. Okay, so L is the loss suffered by h that you have selected on random, let me not confuse you, on samples xi comma yi coming from s. So now the framework is more or less complete. Okay, what we are saying is that okay, there is a learning problem which basically says that given some data, you need to come up with a function h that takes x as input and spits something in this label set as output. Okay, now if this function is good or not is decided by my goal of learning, which is nothing but your loss function. Okay, now when I said that why goal of learning is not included in the learning problem, well, because this loss function could change actually. For example, I can use, we will see later on that let's say for classification there can be several loss functions that we can have, and depending, so each loss function has a different goal of learning. Okay, that is why we need to define goal of learning as something that is different from your learning problem itself. Okay, so so I hope till here we are clear. Okay, that so from now onwards our goal will be to come up with a function h that minimizes some loss function l. That is all. Okay, uh, I don't know, is it clear or is there some issue you want to ask or anything like that? Okay, if not we will move forward. Okay, so what can be examples of loss functions? There can be several examples, so let me just give you one example. So one example could be something like 0 1 loss function. So L, which we denote by L01, okay, which is what? 0 if h of xi is equal to yi. So if your so the function that you chose gives you exactly what exactly the output that was desired, then then there is no loss that you have incurred. However, if you it is 1 if h of xi is not equal to yi. So if the outputs are the predicted value is not same as the desired output, then you incur a loss of 1. This is a loss function that you can use, okay. So I hope the idea is more or less clear. Okay, I think you already know these things because you might have heard of these things here and there, but I am just formalizing them just to make sure that from now onwards we will be working on the same level ground. Okay. So now the next thing, so I will just maybe it is becoming overwhelming. So maybe I will just take 15 more minutes and end this lecture. From next lecture onwards, we will look at other things. Okay. So let me just define few more things. Something which is called risk function. Uh, it is denoted by R of h. Okay, R of h. What is it? This is expected value. Remember now we should be comfortable with expectations. We have seen this in probability theory part of our course. Okay, so expectation is over the joint distribution. What is it? L, your loss function, of y, your actual output, and h of x, the predicted output. This is your risk function, or some people also call it true risk. So what is it? Okay, so remember, if you expand this, it will become L of y comma h of x. The integration will be equal dx dy, something like this, by the definition of expectation. But this people don't write this down, but I just wrote it to uh, jog your memory to what we had seen. Okay. So so in some sense, what is this risk function? Risk function is basically telling you that, okay, if I have samples from this distribution x, so let's say x and y are samples from this distribution, joint distribution pxy. Okay, and now you are giving me some function h. Okay, so the h, this h of x should be your what in some sense should be your out prediction. Okay, so this is your prediction in some sense. Y is my actual output. Okay, so you are also now giving me this loss function L, which measures that if the actual output is equal to or close to prediction or not. Taking expected value over this uh, distribution basically saying that, on an average this function should be good. This is all it is saying. Okay, I hope so. If you remember, we discussed it last time that expected value is actually can be seen as average over something. So this is the risk function is what it is saying is that your your average loss function should, whatever your average loss function is over this distribution pxy, that is my risk. Okay, that is what we are saying. So we want this risk to be less as possible. Okay, so we want that on an average our output is closer to, our prediction is closer to the actual output is what we desire. Okay, this is captured by this true risk function. Okay, however, that one thing that you should immediately think of is that, do we know this pxy? Remember that we saw that we don't know this joint distribution. Okay, in the learning problem itself we saw that this is not known to us. So actually we can never calculate this function. Okay, why? Because this distribution is not known to us. So let me just write it down. Cannot calculate as pxy is unknown. Okay, so I just defined it, but let me write something down. Okay, so now what I will be doing, writing down, is what is called as goal of ML or machine learning. What is the goal of machine learning? Why are we doing all this thing? Let me write it down. So, okay, given a set of training data S that we defined earlier, the idea is to find some hypothesis function. This now I am combining all the definition that we have seen. Okay, so this we saw in the learning problem. Okay, that we have to come up with a function h that minimizes minimizes the risk. What is the risk? Risk is what we saw here. Okay, so mathematically, what do we mean? That we are given some data, training data S, which is actually what? Let's say x1, y1, x2, y2. So these are samples in your training data, xn, yn. Okay, these are sampled IID from PXY that we know, but we don't know what PXY is. Okay, the goal is to find an H star. So generally star is denoted to show the optimal or the best function, okay, H star, which is equal to argmin argmin of H that is coming from H R of H. So what it is saying is that, okay, for all the hypothesis function that are present in this hypothesis class, okay, I will calculate the risk of it. Okay, how will we calculate the risk? By this function. Okay, this is the expression. We will calculate that risk. Okay, now so among all the risk, whichever h gives me the lowest risk. Okay, among all this, so let's say h1 gave me some r of h1. Okay, h2 give me some r of h2, and so on. I will choose the so I will choose h star, which will have some r of h star. Okay, so some risk. Okay, which will be the lowest. Okay, so the risk corresponding to h star will be the lowest. I will choose that h, that hypothesis function. Okay, however, as soon as I say this, you will call me mad, because as I said here, that we cannot calculate the risk itself. Okay, I hope that was clear, that we, since I cannot calculate the risk, this function, how can I calculate the minimum of all the risk? Okay, that is not possible. I hope you can see that. So people said that, okay, it is a sad thing, but they said that, okay, we can do something, something which is, so can we circumvent this problem in some sense? So the idea is to use something called empirical risk minimization, also dubbed as ERM. So what is ERM? So people said that, okay, I cannot calculate the true risk that is here. Okay, I cannot calculate this. So what I will do is I will, calculate a empirical risk. I will calculate some estimate of it. So how is it how will we calculate it? So it is calculated by r hat n of h, that is 1 by n summation from I equal to 1 to n L of yi comma h of xi. And so where are these yi and xi coming from? So xi comma yi, they belong to our training data S. Okay, so here is where our training data is coming into picture. So what I will do is, instead of calculating this average over all the possible x comma y from this distribution pxy, what I will do is, instead I will calculate the loss function only on the data points that are available to me from my training data, and I will take average of it. Okay, and then what I will do is I will take hn hat, which is r. So now I will just use the same definition that I had written earlier for true risk, rn h hat. So this is the goal. Okay, so so the whole story is the following. So ideally what I wanted to do was, okay, I wanted to calculate this risk function for all the possible x comma y pair coming from this. I wanted to calculate this expectation, and I would have chosen that H which gave me the least risk. However, I saw that I don't know this distribution, but I have
Uh,
samples from this
Piyush,
distribution. Yeah.
Piyush, is one second.
Yeah. Was there any question?
Yes, Piyush, I was asking that I was checking, sorry to interrupt, it's not the right
Yeah.
time to bring up, but I was checking that you have not uploaded past lecture. One or two lectures you have not uploaded.
I have uploaded all the lectures. So there were three lectures. The thing was, one of the lectures I had to pull off because there was some internet issue, right?
Okay, yeah.
However, in the next lecture, I recapped everything that was there. So that was lecture three that is uploaded on YouTube.
Yes, because I was looking at them, and for just a revision, and I thought that maybe there was some information missing, so like I thought that would be better to bring it up.
Uh, I think all the lectures are actually uploaded. So the last time we discussed information theory, if I am not wrong. Okay.
Yeah, yeah.
So the that lecture is
Okay,
lecture three. Okay. Uh,
okay.
so this
Because
lecture
we
I
had
have
five
continued from
lectures.
there.
Because we
Yeah,
had
yeah,
five
we
lectures.
had, yeah, we had five lecture. I agree, but if you remember, there was one lecture where there was some hiccup with internet from my
Yeah,
side.
yeah, yeah,
You know,
yeah,
so we had to pull that off. So I think because,
yeah.
however, nonetheless, we recapped it in
Yeah, we
the
covered
next
that.
lecture.
We
Yeah.
covered that. But I was just telling that maybe I was just
Yes.
asking that we are not missing on it, right?
So there is nothing. I am assuring that there is no gap in the lectures. Okay. So if you
Okay,
watch all these three lectures, you will be up to date. Okay.
okay.
Uh, there is no gap. I mean, you will feel that there is continuity and there is no gap. Okay.
And also, when will we allow by taking the lectures?
Alok has not said anything about it to me actually. Can you just maybe ping him once? I don't know exactly.
Okay, no, okay. So, like, maybe I'll call you after this lecture.
Yeah, 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 sure. So, okay, so let me just complete this. After this, that we will end the today's lecture, okay? Yeah, so I was saying that
Yeah,
ideally I
yeah,
wanted to, calculate the risk function for all the sample points x comma y coming from this distribution. However, we saw that, since I don't know this distribution, it is not possible at all to calculate this expectation. So what people did was, okay, they said that, we know that expectation is in some sense average, so I will take some average. Okay, however, I won't take average over all the possible samples coming from pxy. Instead, what I will do is I will take sample average over the samples that are given to me in my training data set. Okay, so this is your average loss function on the training data. Okay, and whichever hypothesis function, whichever h that minimizes this function, this average loss, I will take that function, and I will use that function for my prediction. That is the whole story of machine learning. Okay. So and you will see that in coming lectures, I mean, this is what we will be doing, that we will be calculating this empirical risk, we will minimize it, and whichever function that minimizes it, we will see that that is the best classifier that we can use. Okay, so with this I think maybe we will end. Okay, if there is any doubt, we can take it up, or else we can close the session here. Okay. So this is recorded, and I will upload it on YouTube as well and share it with JSL. Maybe JSL can share it with others.
yeah. Yes, yes.
Yeah.
No, you directly send it in the group now. It will be better.
Okay. So okay, yeah, yeah, there is that group also. Okay, I thought that that group has went dormant, so I didn't upload it there. But
No, no,
okay,
no.
fine. I will.
Yeah, no
I
worries.
will.
Yeah, yeah. Tomorrow's lecture will be after 5 o'clock, right?
Yeah, tomorrow we will do it after 5. So as you said, that uh, Saturday, Sunday morning is fine. However, on weekdays we need to
No,
do it
no.
from
On
in the evening.
Sunday only morning is fine. Because on Saturday also we are having.
Okay, yeah, yeah, yeah.
colleges.
Yeah,
Some
yeah,
of
yeah.
us are in
Sunday
colleges.
morning is fine. Saturday we need to
Yes.
do in the evening. Okay, fine.
Yeah.
Yeah, right. Okay, cool. That
Saturday and
we'll
Monday we
follow
do.
that.
Yeah.
Yeah, yeah, we'll follow that. Okay. Okay. So if there are no questions, I will first of all I will stop the
Yeah.
recording. Okay.